Now let's take a look at combination in more details. So recall our previous scenario in which we looked at the number of ways that the first and second can be selected from 4 athletes. So if you remember this example we solved before when talking about permutation, we had a race competition between 4 athletes and we're just to select the first and the second. So instead of having that, let's assume that we just want to select 2 persons from a group of 4 to form a committee. So instead of having them competing for the first and second position, we just want to select any 2 of them to just form a committee. Let's say a committee that will deliberate on a particular issue. So the possibilities that was given there included A, B, A, C, A, D, like this, and remember how we got all these values. But now think about it. If I want to form a committee, so a committee, let me put this committee here, in which I want 2 people to deliberate on a particular issue, is there really any difference between AB and say BA? Technically there is no difference, and why is that? Because I just want 2 of them to deliberate, so it doesn't matter who I select first. What is of importance is that both of them are in the committee. So having A in the committee and B is the same as having B in the committee and A. So in this case, AB and BA mean one and the same thing, so I can pair them up as just one. Whereas if I was dealing with giving the first and the second position, having A as the first and B as the second is not the same thing as having B as the first and A as the second. But if I'm trying to form a committee, I can see that the order in which I select them does not matter. Similarly, AC and CA mean one and the same. AD and DA mean one and the same. Same with this, this, and this. So if we count the total number of ways in which I can select the committee, what does it become? 1, 2, 3, 4, 5, 6. So if the order doesn't matter, the top and bottom in each column can be taken as 1, as we've done here. So we have what? 6 ways instead of 12. So this kind of selection is referred to as combination, and in combination we are not really interested in the order of selection. What is important to us is that both of them are eventually selected. Either one is selected first or second or third does not really matter, provided that they are all selected at the end of the day. So a combination is a selection of items from a collection such that, unlike permutation, the order does not matter, as I've explained. So from our previous example, we can write it out as 4 combination 2. So 4 combination 2, as we've done out by listing out the possibilities, we know that is equals to 6. So this can allow us to define a general formula. So in general, we can write that n combination r is equals to n factorial over n minus r factorial. The only difference between our permutation formula and the combination formula is that we just included this r factorial. So our n combination r is the same thing as having our permutation formula n permutation r over r factorial. So that is just the difference. This is the permutation formula over here, and I'm multiplying it by just what? 1 over r factorial. So n combination r is the number of ways r objects can be selected from n objects without much regard being paid to the order of arrangement. So an alternative expression for n combination r is given as this. So sometimes you can say an elongated bracket and you have n and r. This also means n combination r. So let's go back to our former expression where we had 4 combination 2. So applying the formula, we know that what n combination r is equals to n factorial over n minus r factorial. So our n in this case is 4 and our r is 2. So that becomes 4 factorial over n minus r becomes 4 minus 2 factorial times r, which is 2 times 2 factorial. And that's equals to, we know that our 4 factorial will be 4 times 3 times 2 factorial. 4 minus 2 is 2 factorial times 2, and 2 factorial cancels out 2 factorial. 2 in 4 goes twice, and I have 3 times 2, which gives me 6. So as we did when we listed that, we have 6 ways in which 2 people can be selected from 4 to form a committee. So let's on our skill by trying to evaluate the following. So first we have 9 combination 6, and we know that that will be equals to 9 factorial over 9 minus 6 factorial times 6 factorial. Again, n is 7 and r is 6, so we just substitute in our formula. So 9 factorial becomes 9 times 8 times 7 times 6 factorial over 9 minus 6 gives me 3 factorial times 6 factorial. 6 factorial cancels out 6 factorial. 3 factorial is the same thing as 6. 3 times 9, which is 6. So 2 goes in 6, 3, 2 in 8, 4, 3 in 1, 9, 3 in 9, 3. So 3 times 4 times 7 gives me what? 84. So 9 combination 6 is 84. How about 10 combination 4? So that will just be equals to 10 factorial over 10 minus 4 factorial times 4 factorial, and that will be 10 factorial over 6 factorial times 4 factorial, and that will be equals to 10 times 9 times 8 times 7 times 6 factorial all over 6 factorial times 4 times 3 times 2 times 1. So 6 factorial cancels out 6 factorial, and when you try to simplify all this, you get 210. So now there are some useful mentions that I would like to examine. So let's imagine a situation where you have 9 combination 9. So what does that become? Applying our formula, we know that what, let me change the color of my marker. N combination r is equals to n factorial over n minus r factorial. So 9 combination 9 becomes what? 9 factorial over 9 minus 9 factorial times 9 factorial. Now that becomes 9 factorial over 9 minus 9 gives me 0 factorial times 9 factorial. 0 factorial, I've told you, is equals to 1. So 9 factorial cancel 9 factorial, and I'm left with 1. So when you have something of the form n combination n, that is n and r are equal, you always get 1. So for example, 4 combination 4 is equals to 1. 100 combination 100 is equals to 1. Provided the n and the r are the same, you get 1. Now let's look at another instance in which you just have 1 at the base. So this becomes what? 9 factorial over 9 minus 1 factorial times 1 factorial, and that gives me 9 factorial over 8 factorial times 1. 1 factorial is 1. So this becomes 9 times 8 factorial over 8 factorial times 1. 8 factorial cancels 8 factorial, and I'm left with 9. So when you have, for instance, n combination r 1, you get n as your answer. So if the base is 1, your answer is equals to n. So for instance, 5 combination 1 will give me what? 5. 8 combination 1 will give me 8. 100 combination 1 will give me 100. You really don't need to memorize all this or to know all this, but I'm just trying to point it out. If you know the formula, you can easily derive it and know what it's supposed to be. So let's take a look at some examples. Find the number of ways 2 prefects can be selected from a class of 15 students. So now you have a class of 15 students and you just want to select 2 prefects from the class. Now I just want to select 2 prefects. It does not matter to me who I select first and who I select second, because I don't even know the position. All I know is that I want 2 prefects. So as you can see, the order in which I select them in this case is of no concern to me, because I'm just interested in selecting 2 prefects. So what does that become? So I know that this just is a classic combination problem, which is what? 15 combination 2, because I'm trying to select 2 prefects from 15. And what would that give me? That would give me 15 factorial over 15 minus 2 factorial, 2 factorial. And what would that give me? That would be 15 times 14 times 13 factorial. 15 minus 2 is 13 factorial, and 2 factorial is 2. 2 in 14 is 7, and 15 times 7 gives me 105 ways. So now there are 105 ways in which I can select 2 prefects from this class of 15. Now, as a side note, assuming I was not interested in selecting 2 prefects, but I was interested in selecting head boy or an head boy and a library prefect on the library prefect. So now I'm still going to select 2 prefects from this, but I want to assign one as the head boy and one as the library prefect. So how is it different from this example over here? The way in which is different is that the order in this case really matters, because selecting student A as the head boy and selecting student B as the library prefect is not the same as selecting student B as the head boy and selecting student A as the library prefect. So in this case, we have to make use of our classic permutation. So we have what? Instead of, we have what? 15 permutation, 2 instead of combination. But in this case, since we are just generic looking for 2 prefects, the positions we are not specific about, we just want to select 2 people. That is why we made use of combination. So the key thing I want to highlight here is that you have to be really careful to know how to tackle a question, and the way it helps me, or the way I figure it out, is to ask my question, does the order really matters? And if the answer to that question is yes, then you know you are going to make use of permutation. But if the answer is no, then you know that you're going to make use of combination. As in this case, the answer was no, because we're just interested in selecting 2 prefects. Either we select A first and B second, or B first and A second, does not matter. So we made use of combination. So you have to take really good note of that. Let's take a look at another example, and these examples are going to be based on some of the ideas we have talked about when we're looking at permutation, but we're going to make use of the combination formula. In this example, we are told to find the number of ways a committee of 5 consisting of 2 males and 3 females. So I write it out. I want to form a committee of 5 people. So this is my committee where they will have their meeting, and the committee must be made up of what? 2 males and 3 females. From a social club consisting of, but in the club where I select them from, there are 7 males and there are 8 females. So in how many ways can I select them? So now, as you can see, I'm just interested in selecting 2 males out of these 8 males, and I'm interested in selecting 3 females out of these 8 females. So you can see that the order does not really matter in this case. Either I select man 1 first and man 2 second, or man 2 first and man 1 second, does not really matter. So this is a classic combination problem. So what do? We find the number of ways in which you can select me. So for the male now, the number of ways in which I can select the male will just be what? 7 combination 2, because I have 7 male and I'm interested in selecting 2 people out of the 7 male. And what would that give me? I have 7 factorial over 7 minus 2, which gives me 5 factorial times 2 factorial. I'm skipping step here because you should have gotten a hang of it, and you can write it out fully if you don't. So 7 factorial becomes, sorry, let me clean this. So 7 factorial now becomes what? Becomes 7 times 6 times 5 factorial over 5 factorial times 2. This cancel this. I have 3. So 7 times 3 gives me what? 21 ways. So there are 21 possible ways in which I can select 2 males from 7 males. How about for the female? So for the female now, I'm trying to select 3 females for 8 females. So that is just going to be what? 8 combination 3. And that will be what? 8 factorial over 8 minus 3 is 5 factorial, then times 3 factorial. That gives me 8 times 7 times 6 times 5 factorial over 5 factorial, and I know that 3 factorial is 6. 5 factorial cancels 5 factorial, 6 cancels 6. I'm left with 8 times 7, which is equals to 56. So the number of ways of selecting the male is 21 ways, and the number of male of selecting female is 56 ways. If you remember, we said that if the number of selecting an item is A or P, and selecting another item is Q, the number of ways of selecting both will just be what? P times Q. So now the number of ways of selecting both the males now and the female, of selecting 2 males and 3 females, will just be equal to the product of their individual combinations. So that will be equal to what? 21 times 56, and 21 times 56 give us 1176 ways. So there are 1176 ways in which I can form this committee of 5. Pretty much a large number, as you can see, and that is the beauty of combination. Imagine having to write it out or list out all the possibilities. We have to list out 1176 ways, which will be very long and tedious, and we're definitely going to make some mistakes. But now with the help of this formula, we can easily simplify it and solve it in less than just 1 or 2 minutes. Let's look at another example where we have some restrictions. So out of 7 women and 9 men, a committee consisting of 3 women and 4 men is to be formed. So now what do we want to do? We want to form a committee, and the committee is going to be made up of 3 women and 4 men. Okay, and the total number of women is what? We have 7 women in total and we have 9 men in total. So we are planning to take 3 women, or select 3 women out of 7 and 4 men out of 9. And you should, as you will note, or you should note, the order does not matter in this case also, because I was interested in selecting just 3 out of them. The order in which I select them is of no particular importance to me. So we are going to make use of combination. So now we are asked that in how many ways is this possible if one particular man must be in the committee. So let's imagine now there's a particular person that we want to be in the committee, maybe because he's more diplomatic or because he has leadership skill and is going to be the head of the committee, but there's a man that we've reserved a spot for. So now we know that we can simplify that committee now. We have 3 women, but now there is already 1 man that his position is already guaranteed. So I'm going to note it as well, G, meaning guaranteed. So what am I left with? That means I'm only looking for 3 male now, because one of those male, his position has already been guaranteed. So I'm going to select 3 women from 7 women, and now I'm going to select the remaining 3 women from how many men? Since one of them has also position has been guaranteed, I'm going to remove 1 from it. So I'm just going to be left with what? 8 men. So the task now is to select 3 women from 7 women and to select 3 women from 3 men from 8 men, because one of those men, his position has already been guaranteed. So for the female, or for the women, let me use women, we have what? We are trying to select 9 out of 7. So we have 7 combination 3. And what would that give us? 7 factorial over 7 minus 3 factorial, which is 4 factorial, then times 3 factorial. And that will be 7 times 6 times 5 times 4 factorial over 4 factorial, and 3 factorial is 6. 6 cancel 6, and 7 times 5 gives us 35 ways. How about for the men now? So for the men, as 1 man's position has already been guaranteed, I'm no more selecting 4 men from 9 men. Now I'm just trying to look for 3 men out of 8 men. So for the men, it becomes what? 8 combination 3. That is what? 8 factorial over 8 minus 5 is 5 factorial and 8 factorial. And when you simplify this, you get 56. So the number of ways of selecting both the male, the women and the men, as we've discussed, is just going to be the multiplication of their individual possibilities. So that becomes what? 35 times 56, and that gives us 1960 ways. So there are now 1960 ways in which I can select 3 women from 7 and 4 men from 9 if a particular man must be in the committee. So to recap, what we first did was we try to subtract the man's position that has already been guaranteed. So he's already guaranteed to be in the committee. So we are no more looking for 4 men. Now we are looking for 3 men because we have already guaranteed the position of 1. And those 3 men will be selected from the remaining 8 people that their positions have not been guaranteed. So we now reverted to our combinations of business as usual. And we are using combination because the order does not matter. And we simplify this to get the men and the women, and to get both of them together, we just multiplied them. So let's take a look at this final example under combination. So a man and his wife are seated in a bench containing 5 people. Okay, so let me draw the bench. So you have the bench over here, and let me see, these are the seats. You have 5 seats, 1, 2, 3, 4. So 5 people can sit down on the bench. If the man must always sit beside his wife, how many arrangements is possible? So now let me call the man. So now since there are 5 people sitting on the bench, I know that it's going to be made up of the man, which I'll represent with M, his wife, which I'll represent as W, and 3 other people, which I'll represent as A, B, and C. So M and W represent man and wife, and ABC represents the 3 other people. So the man loves his wife so much that he insists that he must sit beside his wife. So what does it mean? It means that if the man is sitting down here, for instance, this is an instance, then the woman must be sitting down here also. Let's take a look at that scenario. If the man is sitting down here, his wife must be sitting down here or here. Any one of these will suffice. His wife can be down here, or his wife can also be sitting down here, provided that he stayed close to him. So in how many ways is this possible? So the way we are going to figure this out is through intuition, and there are 2 basic intuition. I'm going to try to solve the more intuitive one and see if I remember the other one so I can talk about it. So firstly, let's take a look at the man. The man and his wife have to sit together. In many ways can the man and his wife sit together. If you think about it, the man and his wife can sit together in what? Since they are sitting together, we can sum them up as just one entity. So let me do it like this. So I can sum them up as just one entity, and I'm left with remaining people A, B, C, A, B, and T. So if I take this as one person, I have what, like I did when I was solving the previous example where we had elves. Remember the example of well. So now I take it as 1. So now instead of having 5 people, I have what? 1, 2, 3, 4, because I've lumped the man and his wife together as 1. So now I can write this out as what? 4 factorial, then times. Now within the man and his wife, the man can sit down first and his wife second, or the wife can sit down first and the man first. They can sit down and interchange, provided they are sitting. So the number of ways in which both of them can be seated together internally is if the man sits first and his wife sits second, or the wife sits first and the man sits second. So that gives us what? Times 2. So this 4 factorial represents taking it together as 1. So we have 1, 2, 3, 4, and while these 2 represents the number of ways in which they can now sit down within themselves, the man first, woman second, or woman first and man second. And when we simplify this, 4 factorial gives us 4 times 3 times 2 times 1 then times 2, and this gives us what? 48 ways. So there are 48 ways in which this arrangement is possible. What is another way to think about it? Another way to think about it is to consider the 3 people sitting together, or the 3 other people. So we have what? A, B, and T. At the end of the day, they both mean the same thing, but are just different ways to think about it. Let me change the color of my marker. A, B, and T. So now the man and his wife can either choose to sit down at this position over here together. They can choose to sit down at this position here together. they can choose to sit down at this position here together, and finally they can choose to sit down at this position here together. So they can either sit down here, here, or here, or here. So the number of options in which they can both sit down together is what? 4. 1, 2, 3, 4. And now within themselves, the man can either come first and the woman come second, or the woman come first and the man second. So within themselves, there are 2 possible arrangements also. How about the other 3 letters A, B, and C? They can both occupy either this position, or either this position. So the number of ways in which they can occupy will just be what? Equals to 3 factorial. So if we sum this up, 4 times 3 gives us 8, and 6 factorial is 6. 8 times 6 gives us 48 ways. And as you can see, we resulted in the same answer, which is 48. So what really matters when you're trying to solve questions is how you're able to think about these things. And the only way which you can master how to think about it is by practice. But luckily, JAMB does not really set questions that are as technical as this. So you might be safe if you don't really understand how to solve some complicated questions. But to be on a safe side, it will be good to know how to do questions or solve questions like this. So as an assignment, I want you to try to list out these 48 possibilities and try to see if you're able to figure it out. It's going to be very tedious, but it's important to do it so you can indeed either prove or disprove that there are 48 ways in which these arrangements can be made. So that pretty much sums up our discussion on permutation and combination. So if there is one thing I want you to put at the back of your mind, is that before you tackle any question, you have to ask yourself the fundamental question: does the order matter? If the order matters, then know that you are dealing with permutation. However, if the order does not matter, then know that you are dealing with combination. This will save you a lot of confusion. And I remember I had this kind of confusion when I was in secondary school also. So try to understand what it means, truly means, for the order to matter and what for the order not to matter. If you truly understand, then it will come naturally to be able to know which formula to apply. So next, we are going to be trying to solve some JAMB past questions.